Welcome to Module 4, Naval Architecture subject, extra first class marine engineering examination as per the Government of India DG shipping rules. My name is Krishna Kumar, former ship surveyor with DNV and Indian Register of Shipping. Module 4 comprises of the following subjects, generally categorized as powering and propulsion. This possibly is a subject where the ship design and the marine engineers, the engine comes in together. So from that point of view, it may be a very interesting subject for a marine engineer. But having said that, I must also say that this part of the subject contains a lot of theoretical background because it relates to fluid dynamics, hydrodynamics, fluid mechanics, and propeller design, geometry, which could be a bit esoteric. But I will try to keep it as simple as possible and relevant, fit for the purpose. Now, what is this issue of powering and propulsion? Simply said, this picture, there is an engine which is driven with the fuel supplied at certain engine operating, which all marine engineers are very familiar. It delivers power to a propeller which produces a thrust which pushes the ship to certain speed. But what has to overcome is the resistance of the ship to achieve that speed. It has to overcome the resistance to achieve that speed, so the power must be equivalent to that to get that speed. And what is this resistance other than the wind resistance, the water resistance? Below the water, you have the resistance due to the frictional resistance, the wave making resistance, and there could be hull fouling. So if you look at this picture here, when any object moves through the water, just like stability is an inherent part of the of a object in the water, wave making is an inherent part of the object when it moves under water. And this leads to a loss of energy of the, or you have to supply that energy to go to at some certain speed. So that is the basis for calculating these things. So if you look at this particular picture here, this shows the total resistance of a ship plotted against the ship speed. So there is a area where the ship speed you can achieve at certain levels of resistance. After that, there is an increase in the total resistance. And if you look at that, the skin frictional resistance has not changed much, but mainly this is due to the wave making resistance which has increased. So if I may simply say that as the speed goes in, more waves are created. So that is expanded, and that is the reason why the resistance goes up. So another way of looking at it is if you look at different types of ship forms. For instance, here is this line shows a normal ship's monohull. So it goes up, there are some optimal speeds, and then the resistance goes up for the ship speed. But had it been a planing hull is a hull which will lift up over when it reaches a speed, and then you can see that up to here there is a resistance builds up, but after that it lifts up, so the resistance comes down, and at a higher speed lower power is required, so the speed can accelerate more. Or you take the ways of a hydrofoil. The hydrofoil, which is this blue line here, hydrofoil relay up to a certain level of speed, there is some level of resistance. After that, the hydrofoil works and the vessel comes out of the water, and then actually the power comes down for the higher speeds. So there are, depending on the ship's form, resistance components can change. Fouling is another area which I mentioned, can lead to increased resistance and thereby more power as a vessel keeps flying. So these are barnacles in a dry dock. The vessel is in a dry dock, people are sitting below and they have to clean this. This could be certain underwater parts where there are live barnacles. So there are various types of hull roughnesses which have to be calculated and taken into account. One could be due to the ship's plates buckling itself, it could be weld seams, it could be paint roughness, and marine growth. So various levels of roughness factors have to be accounted for when you're looking at resistance to estimate the power. Now there are some other aspects which I would like to touch upon. This again borders, as I said earlier, on the theoretical aspects. But what I was so far saying was that the total resistance can be broken up as frictional resistance and wave-making resistance. And there are various coefficients on which you can theoretically estimate them depending on the ship's dimensions, etc. And these are all related to certain principles of hydrodynamics. For instance, there is a Bernoulli's principles of flow. You must have heard about the Bernoulli's law, the Venturi effect, etc. Viscosity, boundary layer. So essentially what it means is that certain power requirements or force requirements depends on whether the flow is lamellar. Lamellar means a flow which is smooth, which can happen in the front of the ship, a smooth flow. It's not turbulent. But at the same time, if you look at the back of the ship, there could be a lot of turbulence from the ship's wake itself. So there's a turbulent flow, and there are some non-dimensional numbers which are used to determine. There is a Froude number and a Reynolds number. Reynolds number, when you do this, which means whether the flow at that particular speed is lamellar or turbulent, these have all got some bearings to determine the resistance and the powering of the ships. But I'm not going to go deep into it. There are a lot of resources on the internet where, if you're interested, you can find more. This is an important topic. So here a ship, as it moves forward, so you can see there will be more lamellar flows in the front of the ship, and as it goes back, there's more turbulent. The wake, the propeller operates in a turbulent field and on the wake of the ship. And the waves are created, and these waves have got the crest and the troughs along. There is one, I would like to point out here that there is one angle given here called 19.5 degrees, and that is called a Kelvin angle. This is another natural phenomenon of anything moving in the water. It creates a wave where you can see this, it comes out very clearly of this, that if you, with the center line, if you plot the flow of this, it will be 19.1 degree would be the flow. It is one way of estimating what is the effect of the wave making. And this is, see some ducks, even a ducks when going underwater where they're paddling with their feet, it also creates this Kelvin angle. This was observed by Lord Kelvin in one of the experiments. That's why it's called Kelvin angle. So you look here, these are waves which are created by the ship's hull, and there are wavelengths between the crest and the trough. Now, for instance, the principle of, and this represents an expended energy from the ship. So in olden times, somebody realized that if you put a bulbous bow over here, it creates its own wave, and you design a bulbous bow in such a way that the wave it creates can go and reduce the wave which the ship's hull creates. Thereby you can reduce some wave making energy. So that is the principle behind the bulbous bow of getting some benefit out of reducing the wave making energy, wave making frictional loss. So on resistance, increasing the resistance. That is why a bulbous bow is provided. So if I may sum up, wave making is a very important component of the whole resistance, total resistance, and wave resistance possibly gets created in the forward part, frictional resistance across the midship, and there's a lot of turbulent actions from the wake of the ship and due to the propeller and in the aft of the ship. But this picture is already explained because this is how the resistance curves can vary based on either it is a displacement vessel, a semi-displacement vessel, or a planing vessel, as was explained in an earlier diagram. So resistance curves determine, to some extent, resistance curve follow the resistance is through theoretical methods. You can also estimate it through model test. Ships' models are defined, and you can directly go and even do the powering estimations of this. And a carriageway in a long towing tank, India also has got some very good testing and towing tanks in Pune, in Chennai, IIT Chennai, and there these kind of calculations can be done. There are theoretical calculations without resorting to a model test can also be done, but model test will give a very better approximations of the powering requirement. So what you see here is a carriage, a towing carriage on which the vessel is moved forward using this, and then you are measuring a lot of, using strain gauges and certain pressure measurements, you are able to estimate the various aspects of flow and forces. essentially at the end of the day, what is interesting is to know what kind of engine power is required. So if you look from a hull perspective, the thrust horsepower of the propeller, or from an engine's point of view, we start from the brake horsepower of the propeller of our engine, then the shaft horsepower is a downside of the reduction gear, and the delivered horsepower is below the bearing seal, beyond the bearing seals and the struts, and the thrust horsepower is what the propeller. So from a naval architect's point of view, they are mainly interested with the thrust horsepower, and all these factors have got efficiency on the ship's drive system. So when an engine is selected and powered, so you start from here and you have to cater for all these efficiency issues. The propeller is another complex piece of machinery, and calculating it is essential principle. It is like a screw propeller on a screw of a normal screw, because it moves, but it's quite different because in a water it has to produce a thrust. So when a propeller, like an aircraft propeller, rotates on certain speed and RPM, that will produce some thrust, and to achieve that it consumes some torque. So torque is given by the engine, and these have to be matched, and that is another very important aspect of the ship design, of getting the design point correctly. And if you look at the propeller shape, it's also very complex because the blade is twisted across 3 dimensions, and olden times we used to make a theoretical model with patterns on that. Now there are computer programs which can simulate the entire, this is drawn through a computer simulated program where you can get the propeller shape and turn it and look at the CAD/CAM principles. Otherwise it used to be much more involved, developing these lines of the ships. Now the simple explanation for the thrust is these are aerofoils. Every part of the blade is an aerofoil shape, and as it hits the water, with the direction of movement of the water, a force is produced, and the cumulative of all the forces produced is the thrust which is produced, which propels the ship forward and pushes the water back. So this is in a nutshell. Now there are calculative methods by which one can estimate the total thrust, the thrust at a point using lifting line methods. There are modern theories of propeller theories, blade element theory, by which you can compute these things using sophisticated computers and algorithms. That is how propellers are designed now these days. Again, this is a very specialized area which I'm not diving deep into. Now, from a simple perspective of a propeller, from a simple estimate of a propeller, one can conceive that one part of the blade of this 4-bladed, it could be part of a cylinder. So you can imagine there are many concentric cylinders, and each part is moving around the cylinder, and then it's a helical path which it will. So using these kind of principles, the computer programmers have defined algorithms on which you can define these, and you can get drawings out using CAD/CAM principles. But what is important to understand is a simple concept of the pitch. The pitch is nothing but how much would the distance travel for one revolution of a blade point. That is the pitch. The lower the pitch, it will travel less. If it's a higher the pitch, it will travel more. That is the theoretical area which will travel if the water was like a wax or something like that. But normally that theoretical part of the blade and the actual path of the blade, there will be a difference, and that's called the slip. So in propeller design, slip is another factor which has to be considered, and that depends on the speed of the ship and the various factors of wake and other things. So these are also part of the ship design aspect. Now the propeller design, this computer software which will help in designing. So this gives even the various kinds of angles, pitch angle, various angles, so that you can define them using this software. It has made it much easier to design propellers, and there are specialized companies and designers who specialize on propellers. Now coming back to the series design which I mentioned earlier, this was how ships are designed, by picking a standard series. Wageningen B series is in Netherlands. They made many propeller types of standard designs, and so before the computer era, this was the method of designing propellers, where there were certain non-dimensional coefficient of torque, the engine capacity, the thrust required from the resistance, and the speed. They used to map certain propeller characteristics in terms of thrust coefficients and power coefficients, and these could be used to design propeller. This is again another specialized area where propeller design, series design is used. And in this case, because when you design a propeller, there are aspects like cavitation, noise, vibration, and of course one has to look at fuel consumption. That again is an interplay between the propeller and the engine. So all these aspects have to be considered. I will not dwell deeper, and there is quite a few parameters you see of a propeller out here, and if you are interested to knowing more, there are many articles on the internet where you can browse and know more. But what is important as a marine engineer to understand is the propeller power curve and its interaction with the engine curve, and the fixed pitch propeller and the controllable pitch propeller. I will just touch a few key aspects of this. An ideal propeller curve has a design point. So at an RPM, there is a horsepower required, and that should meet the engine horsepower. So as a propeller turns at a particular RPM, it requires certain horsepower. Power is equal to the torque requirement, and at that it will produce certain thrust. So there is an ideal design point which is designed. But suppose you fit a propeller which is not correctly designed, a too little pitch, then you cannot have the right fit for the engine power. For instance, at the maximum RPM, it cannot reach the maximum horsepower of the engine, so it's a poor fit. Similarly, if you have too much of a pitch or a diameter also, it's an ill fit, because the maximum horsepower is at a higher RPM. So in a fixed pitch propeller, so you stick to the originally designed, because it operates at a design point at the particular RPM. And as you come down the RPM, naturally the power would be less. This problem was surmounted by the controllable pitch propeller, especially in ships that require to be more versatile. The fixed pitch limitation was avoided by the variable pitch mechanism. So now these are again propeller, this is for one variable pitch propeller. These are the propeller curves at various speeds. The pitch angle and pitch angles, at which pitch angles and speed, you could be at one rotational speed and change the pitch angle and get higher speeds. So you can see that higher speeds you can get at one rotational speed. This gave to a lot of versatility. So, and you can even automate this, that you can get certain speed so that there's no manual intervention required. And the main one limiting factor, if it's a manual process totally, is in getting the optimum fuel efficiency. Now this particular picture shows a controllable pitch propeller at a operating point here, where the particular RPM, this is the power curve, and it is consuming some amount of engine power. But this particular point is away from an optimum fuel efficiency point of view. So at this particular, these show the ship speed. So this is a higher speed where this may not be optimum. So it is better to work at a lower speed curve at another pitch level. So this is how. So by the automatic speed control, these are automatically calibrated and worked. So there is not much of manual, because this curve will be automatically taken so that the vessel will operate at a optimum fuel consuming certain engine load and at the fixed RPM. The engine RPM will also come into the zone of optimum operations. This we mentioned about this fixed pitch propeller, the Wageningen series. So these are non-dimensional coefficients. Again, you can read up a lot on this. There are certain fixed blade area ratios here which are given. 4-bladed series, 3-bladed series, various series are there. And these are well documented and published data available in the open domain. Now, so at the end of this entire exercise of resistance and powering calculation, what comes out is at certain speed, you estimate certain power required to power the ship. That's what it is. There are certain theoretical methods, there are model testing methods, and for instance here what is given is these various methods of calculations. One is a Guldhammer method, there is a Hallstrop method, simple displacement method, and you can even average it out and come. So this will help at, like, if 17 knots is your speed, what would be the effective power needed? That can be estimated. This is the end of a design phase of calculations, for which there are many things. The propeller plays an important part of transferring this into the propeller must be fitted into this powering estimation which is coming from the resistance. So this is how this whole thing ties up: propeller, the resistance, powering, and propeller. So with this we come to the end of this topic, and I think I've covered all the arrangement except possibly a few things on like thrust deduction fraction. These are all certain measures which go into the fine aspects of deduction factors and efficiency factors. And there are even ITTC is the International Testing and Towing Tank Convention, which I will touch next. Ship trials are of essentially two types. One relates to the maneuvering and sea keeping and turning and course keeping abilities. Other relates to endurance trial and validating the operational data. So what was estimated in the design, whether they are correct, what is the ship speed, what's the powering requirements. Ships, I will limit myself because as the next topic on module 5 is about maneuvering. I will touch in that subject some parts of these tests and what they are. But turning circles and Z maneuvers are part of course keeping and course changing abilities. But when it comes to endurance test, normally 4 hours at rated speed is what is an endurance test, and 2 hours at engine speed corresponding to the cruise power. You run the engine at the cruise power for 2 hours and all parameters are tested, and you're measuring the speed of the achieved against the power requirements. You also run the propeller at a higher than nominal speed, 103%, and then see what's the effect of that. And so these tests are documented and available in the sea trial data, which is also published and available on board. There are standard formats in which these are published and standard methods in which these are part of the delivery handing over process. And these are naval architects and marine engineers are jointly involved in taking over the vessel, or handing over and taking over the vessel at the new construction stage, or even after a big modification. So these are just some pictures of maybe a speed trial of a ship, new ships. This could be a zigzag maneuver. This could be a turning trial. There could be other trials. So for example, what you're seeing here is the offshore vessel with the firefighting systems on, and then with that you may do a maneuvering test. You may want to go nearer. So these test protocols are defined beforehand, agreed on, and in a systematic manner the sea trials, which may last for a week, is conducted, and these measurements are recorded and available during the lifetime of the ship. So with this we come to the end of module 4. It is one of the largest modules in this 5-part series on naval architecture for extra first class. I hope this has been useful to you. Thank you very much.